So if we see the production of nitric acid PFD, then we can have the raw materials as NH3 and the air. So here you can see the NH3 from the storage. So ammonia already we have produced by the synthetic gas. So that will come over here to form the nitric acid. So the ammonia from the storage and the compressed air, so they are mixed. So 10 volume percent of ammonia, 90 volume percent of air, and the pressure we kept at 3.5 atmospheres. So it will come in atmosphere, the reactor, then it has a temperature of 800 degrees Celsius, then the superheater and the heat recovery boiler. So the superheater, the whatever the reaction heat is evolved, so that is sent to form the steam. Then heat recovery boiler, it will recover the heat produced in the overall reaction. So then we have the catalyst recovery filter. So whatever the catalyst is over here, suppose the traces are coming over here, then we can recover in this one. Then it is cooled and it is sent to the oxidation and absorption tower, which was at 40 to 50 degrees Celsius. So here what we are doing, so whatever the heat producing over here, that we are recovering in this one, and then tail gas heating process and this steam economizer. And then again we are cooling with the help of water to get the NO in this reactor. So in this one, the NO, then air is added to form the NO2. So this reaction will take place at 40 to 50 degrees Celsius. And then whatever the nitric acid we are getting, that we can send to the storage. So here what happens, the 93 to 96% yield we can achieve, so by the process conditions. Then what we have, the tail gas heater, so we are sending to this one the expander, and here we can see the turbine. So here the whatever the heat recover, that we can send to this one for the process steam recover. And then here makeup water is said to convert the steam. So main thing is the ammonia and air at compress at 3.5 atmosphere sent to the reactor to form NO, and then it is cooled in stages, and then with water again to achieve the temperature of 40 to 50 degrees Celsius, where NO and NO oxidized to NO2, which we can have the reaction with water to get the HNO3 in 50 to 60% of nitric acid, that we can further concentrate with the use of sulfuric acid or MgNO3. So here what are the major engineering problems? So here thermodynamic and kinetic consideration, if we see, then NO formation at high temperature but NO2 form NO at a low temperature. So here we have seen earlier the ammonia to NO formation. So here the temperature is very high. So we have to cool in stages. So these are the three stages where we are cooling. So this takes place at very high temperature, whereas this takes place at a very low temperature. So to get NO and here to get NO2. So this is the one of the thermodynamic equilibrium problem. Then the reaction kinetics of this is favored by high temperature and pressure, the good catalyst diffusion to catalyst surface. So the NO formation is favored by the high temperature and pressure. Then if you have the good catalyst and the diffusion rate of the gases to the catalytic surface is good, then we can have the higher conversion. Then the reaction rate is directly proportional to the lower temperature, the high pressure for catalyst, and NO2 concentration in the gaseous phase. So here the heat is evolving, so we should have the lower temperature, but it should not be so low so that no conversion taking place. And then high pressure is needed so that diffusion will be high. So here if we see, the reaction catalyst is favored by the high temperature but not too high. Because of too high temperature and too low temperature, the conversion will be less. So as the reaction is the exothermic, the low temperature compare is always essential. Then high pressure to have the gaseous particle to the catalyst. So more the gas particle to the catalyst, more is the reaction rate. And the NO2 concentration is high in the gaseous phase, it will favor the reaction and we get the good quality of the nitric acid. Then if you see the economics of this nitric acid, then nitric acid used mainly in the fertilizer industry. Then the nitric acid is used to form the ammonium nitrate with the reaction of the ammonia, and this is the major part of the explosives. Then other nitrate based explosives we can manufacture with the help of nitric acid. Then it is used in rocket propellant composition. So in India, if we see, the major producers are the Deepak Fertilizers and Petrochemicals Corporation Limited, then Deepak Nitrate Limited, then JNFC, that is Gujarat Narmada Valley Fertilizers Corporation, and Hindustan Organics Corporation Limited. So the next chemical we have to study is the urea, and it is nothing but, so acetone structure we have seen, the CH3COCH3, so instead of CH3 if you have the amine, so that will give the structure of the urea. So it is represented by the NH2CONH2. So generally it is in the granular forms used in the fertilizer industry. So it has a molecular weight of 16.05, then melting point 132.7 degrees Celsius. Then it decomposes at high temperatures, having the specific gravity of 1.335, and it's fairly soluble in water. So solubility at 20 degrees Celsius is around 110 gram in 100 grams and 135 grams in 100 grams at 100 degrees Celsius. So grades we can find the fertilizer granular and coated with the non-hygroscopic dust. Then the liquor mixtures of urea in NH2 solution, and the slow release for the low molecular weight urea polymers. So we can have the fertilizer grade and liquor mixtures, and then for the slow release in the soil we can have the low molecular weight urea polymers. Then if we see the consumption pattern of the urea, it is used as a solid fertilizer 53%, and the liquid fertilizer 31%. Then we can use to feed the animals and to form the formaldehyde resins, melamine and adhesives. Urea formaldehyde resins as plywood resins. Then melamine formaldehyde resins are used as dinnerware and for extra hard surfaces. Then melamine by condensation of the urea, and urea is the largest produced in nitrogen industry. So this is the major product of the nitrogen industry. Then what are the different methods of production? So we have the ammonium carbamate decomposition method. Then ammonia and carbon dioxide compressed and reacted at 100 to 200 atmosphere pressure and at around 170 to 190 degrees Celsius to form the ammonium carbamate. So here you can see the structure of the ammonium carbonate, NH4, CO and NH2. So after dehydration means H2 from this NO, so H2O if we evolve, then we get the ammonia, the urea. So dehydration of ammonium carbamate in low pressure stripping section produces urea, and recycle of unreacted reactant to achieve high conversion and yield. So this is the ammonium carbamate decomposition method where we are reacting NH3 and CO2 at this pressure and 170 to 190 degrees Celsius. Then by forming the ammonium carbamate we are decomposing to evolve the water and we get the urea, and whatever the unreacted material we are again recycling to achieve more conversion and more yield. So the chemical reaction if you see, so carbon dioxide and ammonia they are used to form the ammonium carbamate. Then that carbamate is decomposed to form the urea with the evaporation of the water. So this is endothermic process, and the undesirable reaction also formed in this process, that is the urea form this biurate. So biurate is the byproduct and which is undesirable byproduct of this reaction. So the raw materials and the quantity requirement if you see, then raw materials are carbon dioxide and ammonia. Then if you are forming the 1 ton of pure urea, that is 99+% purity. So we have the NH3 1.15, then CO2 1.47, the power consumption is 210, then cooling water 120 tons, and the steam requires 1.8 tons. Then plant capacities being 100 to 1500 tons a day. So process is the Montecattini solution recycle the ammonia and carbon dioxide are compressed separately and added to the high temperature autoclave, which is water cooled. The average residence time is 1.5 to 2 hours. So the mixture is taken at highly compressed and it is sent to the autoclave where it is resided for the 1.5 to 2 hours to carry out the reaction. This liquid effluent let down to 27 atmosphere and fed to the flash evaporator, which separates gas and liquid. Unreacted gases are recycled. Carbamate is decomposed in atmospheric flash drum. So the mixture taken, compressed and fed to the high temperature autoclave, and there it will rest for 1.5 to 2 hours. Then whatever the product form is let down to 27 atmospheres and it is separated, gas and liquid is separated. Then the carbamate is formed, it decomposed at the atmosphere flash drum, and the unreacted gases is sent back to the reactant mixture. So urea 80% aqueous dried in a vacuum evaporator and it is dried up to the 1%, and urea in the motor form sprayed in a solidification tower to get prilled, and the temperature kept just about melting point for 1 to 2 seconds to avoid biuret formation. So this is the major problem. You have to keep the mind the temperature is above, then it can form the biuret, which is the undesirable in the reaction. So this is the flow diagram for the urea formation. So we have the ammonia and the carbon dioxide. So here we can see the ammonia 3 to 5 moles and the carbon dioxide 1 mole. So they are compressed separately, then they are fed to the reactor. So urea synthesis autoclave and it is kept at 180 atmosphere and it is water cooled as mentioned. Then here the residence times will be 1.5 to 2 hours. Then whatever the product form, so that is sent over here and in flash evaporator at 140 degrees Celsius and 27 atmosphere. In flash evaporator, the whatever the mixture, it will be separated. The gas and the liquid mixture is separated. So gases which contains the ammonium carbamate and the ammonia, the CO2 and H2, so they are sent to the recycle again, and whatever the liquid mixture, it is fed to the condensate. So from here it will go to the flash drums, and where we can have the 80% aqueous urea for nitrogen liquor products, or we can have them in another vacuum evaporator, so 60 centimeter of Hg and 135 degrees Celsius. So here, so already flash evaporated, and then we can have the flash drum at 1 atmosphere for the decomposition. Then after decomposition of the ammonium carbamate, what we get is urea. So urea we can either have in aqueous form, that is 80%, which we fed to into liquor, or we can have the another vacuum evaporator which will separate, and we can have the molten urea. Then this urea is sent to the prilling tower, so it is sprayed. With the help of the air it will be solidified. So these prills we can bind into the urea granules, and it should have the less than 1% of the biuret. So the molten urea, with the help of cooling air, we can prill them with the help of spraying, and we can have the urea granules which contains less than 1% biurets. So here CO2 and H2 separately compressed, fed to the reactor for 1.5 to 2 hours, which gives the ammonium carbamate. Here the unreacted gases and ammonium carbamate is separated. The condensate and the unreacted gases, they are sent back to recycle, and whatever the ammonium carbamate is again sent to the flash drum, where it will decompose to urea. So it is sent as the aqueous urea or the molten urea. We can have the vacuum evaporator, where we get 99% molten urea, which can be prilled in the prilling tower. So here whatever the NH3 and CO2 off gases, so they are sent to the NH3 byproduct uses, or they can recycle back to get the more conversion to form the urea. So here the major problems are the autoclave variables. So you have to keep in mind the temperature is very essential over here, otherwise we get the biuret formation. The carbamate decomposition and recycle. So this is essential to get the urea. In the production of granule urea. So in this one, the granules which is formed, so we have to keep in mind the temperature is not exceeding and we get the biuret formation less than 1%. Then heat dissipation in autoclave, as this is the exothermic reaction, you have to take care of the heat evolved in the reactor tower. And the next one is corrosion problem. So corrosion is high because we are feeding the reactor at very high pressure. So ammonia and other gases, they are highly corrosive. So we have to look for the material of the construction, and that will lead to the high cost. So generally stainless steel is used to avoid the corrosion problems, but that will lead to the high cost of the overall process. Then design modification is suggested. So these are given in very well detail in the Dryden. So just mentioning the one-through process, then hot recycle process, inventa process, chemical process, then the solution recycle process, Pechine process, then Dutch state mine process, then allied chemical high pressure process, and Toyo cohesive process. So these are mentioned. So design modification. So whatever the process flow diagram we have seen, so in this one, this mention the little bit variation, so that you can read in the Dryden. If you see the economics of this urea, so urea as a fertilizer and high in nitrogen and replace ammonium salt, causing acidity in the soils. So it is used as the fertilizer and it has the very high nitrogen content, and it has replaced the ammonium salts which were causing the acidities. So earlier the ammonium salts they were using as a fertilizer, but because of the salts and the high acidity, these are replaced by the urea. Then it can be easily granulated or form a low molecular wet polymer for slow release in the soil. Industrially, used for plastic, urea formaldehyde and urea melamine types. Then animal feed, it's a 40% protein requirements in cattle, and the rest can be by low cost carbohydrates. So where the animal requires the high protein diet, so we can use the urea in the protein diet, and the rest we can supplement by the low cost carbohydrates. But it can be happen in countries where urea is cheap and abundant. So India is not the case. India we don't have the urea in abundant form, so we can use for the cattle feed. But where it is in abundant and cheap, we can use as a protein substitute. Then urea produced with the ammonia production plant has a major investment as per today's market. So here what is happening, the urea is produced in the ammonium production plants. So the both plants together can have the major economy. The next chemical we will study is the ammonium nitrate. So it has the ammonia molecule and the nitrate molecule over here. So it has a molecular weight of 80.05, melting point 170 degrees Celsius, and it decomposes at 200 degrees Celsius or higher, and it has a highly soluble in water, that is 900 grams per liter at 20 degrees Celsius, and also soluble in alcohol and ammonia. We can have the white hygroscopic crystals or granules, and the fertilizer 93 to 95% and containing 33% of the nitrogen in it. Mainly it is used in explosive when mixed with combustible materials or exposed to a high temperature. So the ammonium nitrate is mainly the part of the explosive and the fertilizer industry. If you see the consumption pattern of the ammonium nitrate, so it is used as fertilizer because it is high in nitrogen. So it has 33.5% of the nitrogen present in it. Little is in India as nitrogen from it of a poor quality and hence need to be converted to nitro lime or nitro chalk. So in India it is converted into the nitro lime and nitro chalk. So the calcium ammonium nitrate and ammonium sulfate nitrates. So that is the nitro chalk, the types we have in India. Then 12% used in explosive and more than 75% of the explosive use ammonium nitrate. So if you have seen the bombs and the explosives which we have, so the major ingredient of them is ammonium nitrate. And if you see the method of production, so all processes are based on the reaction of nitric acid and the ammonia. So you know the ammonia NH3 and the nitric acid HNO3. So by combination of them we can form the ammonium nitrate. So method variation in products as pellet, crystal or flakes. So here the raw materials are the same, but the final finished product, they may be in a pellet form or in the crystal form or the flakes. So that will vary the process. So the chemical reaction is simple. The ammonia and nitric acid gives the ammonium nitrate with the evaluation of the heat. So the raw material are 57 to 60% of nitric acid from oxidation absorption tower, then liquid ammonia, then clays such as diatomaceous earth and kieselguhr for coating on end product to avoid explosion. So ammonium nitrate is highly explosive. So the final product which we get, so we have to coat them. So you can find in every process flow diagram, as soon as we get the ammonium nitrate, we have to coat with diatomaceous earth in order to avoid the explosions. If you see the quantitative requirements, so if you are producing 1 ton of ammonium nitrate, that is 98% yield, then the ammonia required is 20 tons and the nitric acid requires 1.38 tons of 60% purity, and the plant capacity is being 100 to 500 tons a day. So this is the process flow diagram for the ammonium nitrate production. So you can see it can be either in pill form or to produce the nitrolime, or it can be in the flakes form. So that will give you 3 different processes. So here you can see the ammonia, liquid ammonia, and here is the nitric acid. So they are mixed, then they are reacted over here, and the reacted mixture, the ammonium nitrate will be formed, and that is sent to the vacuum evaporator. So the gases and the ammonium nitrate, that will be separated. So that is again sent to the pilling tower. So the pilling tower, the condition air, it will dry, and then the screening, it will screen, and then the steam heated conveyor or dryer, that will pass them to the coating drum where it is coated to avoid the explosions. The fines are recycled back and we get the NH4 NO3 pills. Or the ammonium nitrate, the 95% solid and 130 degrees Celsius, we can have with the help of pulverized lime. Then we can send to granulator where it granulates, then it is dried, and then it is set to the crushing rolls. So suppose the size is more than 4 mm, then they are recycled back, and when we get this size, desired size of 2 to 4 mm granules, then we will send to the coating drum. Then with the limestone dust, we can have the coating over them and we can send them as a nitrolime. And then the particle which is less than 2 mm, we can send to the classification circuit. Then when you want the ammonium nitrate flakes, then they are preheated, then they are sent to the vapor phase reactor at 230 degrees Celsius, and then molten ammonium nitrate is sent to the separator where it separates the gases and the product. Then it is sent to the flow controller and then condenser. Then the water percentage is removed over here. Then they are sent to the grinder. So you can see the roll over here, and they are converted into the flakes form. And then it will be screened. The fines, they will be recycled back, and then they are coated with the clay, and they can pack as the NH4NO3 flakes. So here, the whatever the separated gases are unreacted, they are sent back to the recycle. So if we see this process again, then it is reacted over here, then gases mixture is separated, then they are filled over here, then they are screened, the fines are recycled back, then they are coated, and they can pack as the NH4NO3 pills. Or the ammonium nitrate taken over here in pug mill or screw mixer, then they are granulated, then they are dried, they are screened, then 2 to 4 mm granules they are packed, whereas the more than 4 mm they are again recycled to get the desired size material, and less than 2 mm we are sending for the classification circuit. Or we can have the molten NO3 over here, and from the vapor phase reactor at 230 degrees Celsius, they are separated and then they are grinded, and the flakes which are formed, they are coated, and we can have the final product as ammonium nitrate flakes. So if you see the pilling process initially, so reactants reacted in the stainless steel reactor, 75% and the 140%, 140 degrees Celsius solution sent to the evaporated to make it 95% solid. Then hot liquor sprayed from the top of the pilling tower counter current to flow conditions air, and the solidified pills must be screened and dried before coating. The fines and overside material is recycled back. So if you see, so this is mentioning about this pilling tower. So here the conditioned air is flow in the counter current flow. So the solids will come from this one and air will come from this side. So the counter current air flow will dry the ammonium nitrate. The next one is crystallization process, which is not shown in PFD. It is same as the previous up to this spraying. The liquor from the vacuum evaporator contains 80 to 85% solid fed to the vacuum crystallizer. Crystal grows of desired size at 40 degrees Celsius for fertilizer use. Then crystal 40% centrifuge and liquor returned to the evaporator. Crystal dries in a rotary dryer at 15 degrees Celsius and coated. So up to this spraying and sending to the prilling, it is the same process. But here we are allowing crystal to grow of the desired side, and the liquor we are recycling back. Then the crystal we are drying, and then we are coating and then pack. Then this triangle process, ammonium nitric acid are preheated at 140 to 150 degrees Celsius and 60% HNO3 at 95 degrees Celsius in stainless steel, and 160 degrees Celsius in tantalum unit to avoid the corrosion by temperature. So ammonia at this temperature and 60% HNO3 up to this temperature in stainless steel and then 160 degrees Celsius. Then water vapor at 200 degrees Celsius removed in cyclone separator, slurry dried, solidified, and unwanted recycled and coated. So this is the technical process we have seen in the process flow diagram. Then modification to produce nitro lime. So 95% melt used for this process. Pulverized lime is added, dried up to 0.5 to 0.6% water and coated with clay. Then particle more than 4 mm recycled, less than 2 mm returned for the size buildup. So here we have seen the nitro lime production. So the pulverized lime will come and then in granulated it will granulated, and with the help of limestone dust they are coated and then we can pack as a nitro lime. So more than 4 they are recycled here and less than 2 for the size buildup. And this we have seen as a standard process where the molten ammonia is created and the separator which separate the gases, and we can have the final product as the ammonium nitrate. Then the major problem in this one is the corrosion problem by the NH4NO3, then the crystallization in the crystallization unit, then safety because it is highly explosive and conditioned air requirements. It should not have any contaminant, and with the conditioned air should be such that it is free from contaminant and it can dry efficiently. If you see the economics of this process, ammonium nitrate because of the high leaching not used in directly but as an intermediate for the nitro lime and the ammonium sulfate nitrate, then desirable to produce with other fertilizer to produce mixed fertilizer. So separately having this plant is not economical, but we can have the plant with other fertilizer in order to produce the mixed fertilizers. Then this triangle is cheapest and safe of all and produce with the nitric acid plant. So when we have the nitric acid plants nearby, then we can produce this economically. Then the other important chemicals of the nitrogen industry are the ammonium chloride, which can form by reaction with HCl and ammonia. So this is used as fertilizer for rice and other crops, but in limited due to the high chlorine content. Pure ammonium chloride used in dry cells manufacturing, also as a flux in galvanizing and tanning industries. Then it is used as the expectorant in cough medicine. Then ammonium chloride is used in the textile and leather industry in dyeing, tanning, textile printing, and to luster cotton. And the ammonium sulfate, so the reaction with the sulfuric acid, so it is used largely as the artificial fertilizer for the alkaline soils. So being this acidic, the alkaline soils we can take care of with the ammonium sulfates. Then in this soil, the ammonium ion is released and forms a small amount of acid, lowering the pH balance of the soil while contributing essential nitrogen for the plant growth. So the same we discussed, if it is acidic, it will lower down the pH, it will maintain pH and also it will reduce the nitrogen in the soil. In the biochemistry, ammonium sulfate precipitation is a common method for purifying proteins by selective precipitation. So in the purifying proteins by selective precipitation, we can use the ammonium sulfate as a initial reactant. Also it is used in a flame retardant. If we see the ammonium phosphate, it is the salt of ammonia and the phosphoric acid. It is soluble in water and the aqueous solution on boiling loses ammonia and the acid phosphate. So this is the mixture form when you boil them. Then ammonium phosphate is used as an ingredient in some fertilizers as a high source of the elemental nitrogen. It is also used as a flame retardant in the thermoplastic composition, and it is used in bread making to promote the growth of the yeast. So it is one of the nutrient for the yeast growth. The next one is sodium nitrate, NaNO3. So it was used extensively as a fertilizer initially and also as a raw material for the manufacture of the gunpowder in late 19th century. It can be combined with iron hydroxide to make resin and also used in a wastewater industry for facultative microorganism respiration. Then it is also used as a food additive, used as a preservative and color fixative in cured meats and the poultry industry. Then the potassium nitrate is mainly used in fertilizer, and it is a good source of nitrogen and potassium, two of macronutrients for the plants. And when used by itself, it has an NPK rating of 13,044. So itself it gives NPK as 13 and 44. Potassium nitrate is an efficient oxidizer, producing lilac colored flame upon burning due to the presence of potassium. It is used in the fire extinguishing in some toothpaste for sensitive tooth. So for sensitive toothpaste are coming, so KNO3 becomes one of the ingredients of them. Then the lastly cyanamide, so CN2H2. So this is white solid, is widely used in agriculture and the production of pharmaceuticals and other organic compounds. It degrades via hydrolysis to urea, an excellent fertilizer. Then microorganisms such as bacterium, myrothecium, then Verrucaria, and they accelerate this process utilizing the enzyme cyanamide hydratase. Also used an alcohol deterrent drug in Canada, Europe and the Japan. So the main references are Diodans, then chemical process industry by Shrews. Also for the use, you can refer the Wikipedia, which is accessed on 8 January 2012.